Hey everybody, Matt Omari here, and in today's video, we're going to review a very interesting looking integral. We're looking at evaluating the integral of the square root of x, of the square root of x, the square root of x, and so forth. And in this video, I'm going to go over two solutions. One solution is going to be very quick and simple and pretty elegant, and the other solution is one I thought of on my own. It's more complicated, but I do think it's worth seeing because it's a more of an interesting approach. So let's just get right into the problem. All right. The first thing we need to figure out is how we can rewrite this expression here and make it simpler, right? And what we're going to do is use a little trick. I'm going to say that y is equal to the square root of x of the square root of x, continuing. But if you look closely, you'll notice that inside of this first square root of x, we have our original expression, right? We have inside this square root of x here on the outside, we have inside here square root of x of the square root of x of the square root of x of the square root of x, and so forth, which means that this expression here is equal to y, which means that we can rewrite this expression or equation we have as y is equal to the square root of x times y, and we're just going to solve for y. We're going to take the square of both sides to get y squared is equal to xy. Then by dividing both sides by y, we get y is equal to x. So if we say that this integral up here is equal to I, I'm just going to set this equal to I so I don't have to rewrite everything. Then I is equal to the integral of x dx, or antiderivative of x, and just using basic rules of integration, this is just going to be equal to x squared over 2 plus c, right? When you anti-differentiate x, you're going to add 1 to its exponent. Since there's no exponent here, we just treat this as x to the first power. So by anti-differentiating, this is going to be x squared, and then divided by the new exponent, which is 2. And this is the solution. The calculus of this problem is easy. The trick was the algebraic manipulation, but once you understand this process here, which can also be used for a lot of other problems that involve nested expressions, then the solution becomes not too hard to find. All right, now for the second method I used, we're going to use exponents in geometric series. Now, in this case, I do have everything already written out. And what I like to do when I look at problems with some sort of complicated expressions or just hard problems in general is just look at simpler cases and see if I can notice a pattern, which is what I did here. So we know that the square root of x is x to the 1/2 power, right? So if we look at the square root of x squared root of x, that's the same as x times x to the 1/2 power to the 1/2 power. Using the properties of exponents, this is x to the 1/2 power times x to the 1/2 power to the 1/2 power, right? You take both of these factors to the 1/2 power because that's the exponent on the outside. And then to simplify this second factor here, we're going to use another property of exponents where you multiply these two exponents here, which would give us x to the 1/4 power, which means that we end up with x to the 1/2 power times x to the 1/4 power, which is equal to the x to the 1/2 plus 1/4 power. These two exponents have the same base, different exponents, or just in general, when you have two exponential expressions with the same base, we multiply them together, you just add the exponents together. Now, yeah, there's a specific reason why I did not simplify this sum here, which you'll see in a minute. Now, if you look at this third expression here that I wrote, I didn't go through all the details of the calculation, but this is x to the 1/2 plus 1 over 4 plus 1 over 8 power. And, if you look at the exponents of these three expressions here, you'll notice a pattern with the sums. And that is, well, one, each time we add a nested square root, we add one term into the sum of the exponent. And the second pattern is that with each successive term, the term is equal to the previous term times 1/2. In this case, for the second expression here, 1 over 4 is 1/2 times 1/2. And then here, this new term is 1/8 in the third expression, and 1/8 is 1/4 times 1/2. So if you're familiar with algebra, or if you've seen this in your algebra class, then you might recognize this as a geometric series. Now, geometric series is a sum of geometric terms, and that's just a fancy term to mean that each new term is just the previous term but multiplied by a constant factor. In this case, that constant factor is 1/2, which means that we can rewrite the terms in the sum as a formula based on geometric sums. Now, if we have this nested square root n times, then that means that this expression here is going to be equal to x to the sum, and here I use the summation notation, the sum from I is equal to 1 to n of 1 over 2 to the I power. And if we have an infinite nested expression, then we have an infinite sum. Then that means that this infinite nested square root expression is going to be equal to x to the sum from I is equal to infinity of 1 over 2 to the I power. Now, in order to evaluate this infinite sum, we're going to use the geometric sum formula. So if you have a sum from I is equal to 0 to infinity of AR to the I, that's going to be equal to A over 1 minus R, where R is just the factor that's inside the exponent, and A is just some constant that this expression is being multiplied by. In our case, this is our R. R is equal to 1 over 2, but as you can see, there's no other factor here. So A is just going to be equal to 1. And essentially, yeah, all we have to do is just evaluate this sum in order to find the value of this exponent, which will allow us to continue and solve the problem. So here I wrote let R is equal to 1/2 and A equal to 1. Then we have the sum from I is equal to 0 to infinity of 1 over 2 to the I power is equal to 1 over 1 minus a half. 1 minus a half is a half. 1 divided by 1/2 is 2, which means that this sum is going to be equal to 2. Now, at this point, you might be thinking, hey, Omari, what the heck is going on? Shouldn't the exponent here be 1, since that's what we got last time? Well, you'd be correct, but you have to pay close attention here. Notice how I wrote the sum from I is equal to 0 to infinity. In the expression we have inside this exponent, we have the sum from I is equal to 1 to infinity. So we're going to have to write this sum in terms of this sum in order to find the value of the sum we want, which is going to be this one right here. And I have that written. We know the sum from I is equal to 0 to infinity of 1 over 2 to the I is equal to 1. Here I wrote 1 because this is just going to be the first term in the sum. 1 is just 1 over 2 to the 0, right? And 1 over 2 to the 0 power is 1. So we have 1 plus the sum from I is equal to 1 to infinity of 1 over 2 to the I. Since we already evaluated this expression here on the left, it's equal to 2, right? We're just going to substitute 2 for the left side, which means that we get the equation 2 is equal to 1 plus the sum from I is equal to 1 to infinity of 1 over 2 to the I. Therefore, that means that the sum from I is equal to 1 to infinity of 1 over 2 to the I is equal to 1. That means that this expression here is 1. So, square root of x, square roots of x, square roots of x, continuing, is all equal to 1. And from here, you would just integrate x dx. That part is the simplest part of the problem. Pretty straightforward, so there's no need to show that again. All right, guys, so those are the two solutions to this very interesting integration problem. If you have any comments, suggestions, or feedback or questions, please let me know in the comment section. I would love that. Also, if you have any alternative solutions that you've thought of, let me know those as well. Otherwise, I will see you all in the next video. Have a great day, and I'll talk to you later. Bye now.